The story you're about to hear this evening is perhaps the best kept secret of the entire Civil War. You will not find it anywhere in any history book. And its prime mover, Major Edward Bissell Hunt, gets a brief mention and always as a failure. And I think you'll see that his project was anything but a failure. First evidence we have of this project comes on the 28th of March in 1862, when the Secretary of the Navy, Gideon Welles, receives a letter promising a revolutionary system of submarine warfare. Now, Welles is inundated with letters like this, some from intelligent officers who have good plans that might be followed up, a lot from crackpot inventors. The vast majority of them end up getting pitched. But Welles pays attention to this letter, not so much because of the writer, but because all the signatories. Some of these names will be familiar to you, some won't. It's a who's who of scientists and engineers in the Army and the Navy in 1862. Welles is a little disconcerted to find that even his assistant secretary has been privy to the project before him, and signs the letter. But he's intrigued enough in a weapon that promises some sort of advantage on the ocean. And the reason for that is Welles fears, along with the entire Lincoln administration, that we are on the verge of a world war. Obviously, we know we're fighting the Confederacy, and we expect the Brits might come in to help them. The French might also, along with their proxy government down in Mexico. What a lot of people are unaware of is that quite possibly the Belgians and the Austrians were going to get pulled in on that side as well. And we had sort of a on-again, off-again alliance with the Russians. Either way, this was going to be a war at sea. Welles is looking for any sort of advantage he can get in the anticipated battles to come with the fleets of all these countries. Now, the letter writer, he may have recognized his name, even though he's an Army officer. It's Lieutenant Edward Bissell Hunt. He's one of a small group of younger officers that basically preserve the forts that guard the channel into the Gulf of Mexico. He's called one of the saviors of the Gulf. He's in charge of completing Fort Taylor, which is in Key West, and it really is held for the Union only because of Hunt's efforts. He's 40 years of age. He's only had 2 to 3 years of formal education in upstate New York. He's from the Genesee Valley in the western part of that state. And yet he graduated number 2 in his class from West Point. And the fellow who graduated number 1 said, really, Edward should have been number 1. He's worked for a long time in the Coast Survey. The Coast Survey is a military and civilian organization. It's the most scientific organization the federal government sponsors. These are the guys that chart the coast, literally as it says, Coast Survey, all the beautiful maps from before the Civil War that allow our ship to navigate accurately up every little creek and along the coast. This is because of the Coast Survey. Hunt thrives in this environment, detail and data driven. He's also a scientist. He has spoken many times to the annual meeting of the American Association for the Advancement of Science on a wide variety of topics, the most impressive of which is the bottom one, a theory of molecular physics. He never wrote a paper on this, but from what he shared with fellow scientists and friends, they said Edward's theory explains everything from atoms to the universe, and they pushed him to try and complete it. It's one of 2 things he will not complete. Now, what got Hunt thinking? When he writes that letter to Welles in March, one of the few lines in it that tells us something critical, it's a very sparse letter, is having during the last 6 months matured a system of submarine warfare. So what happened 6 months before that letter? Well, what happened is a rather ignominious little battle for the U.S. Navy. It's called Pope's Run after the commander, and it's sort of a reference to Bull Run, which we figured we had lost. On that day, on the 12th of October, 1861, the CSS Manassas comes down and bounces the blockading squadron. It rams the USS Richmond, doesn't sink her, but gores her. Richmond goes to Key West for repairs. And you may have noticed one of the signatories on the letter that Hunt sent is the surgeon from on board Richmond. So I believe that Henderson, Dr. Andrew Henderson, told the story of the ram to Hunt. Of course, the other officers told him about it too, and they're a little disconcerted. Basically, anything we had, the Yankees had that could fire at this thing didn't really matter too much at all. The obvious answer to the surface Navy, surface sailors was to make bigger and better guns that will fire bigger and better shot and shell and pierce heavier armor, which leads to the never-ending cycle here, a new arms race, better armor, better weapons, on and on and on. But there is a weak point on all these ironclads, and that's the Achilles heel, the wooden hull below the armor. If you can find a way to reach that, you don't have to battle through all that iron up top. You can sink her with 1 missile. The problem is getting a missile down there. There's a couple approaches, three approaches really in the Civil War. One, of course, is a spar torpedo. This is what Hunley used. What I'm showing here is a Confederate David. It's a torpedo boat. We had torpedo boats also, service ones. This is semi-submersible. The danger there, of course, is that bomb on a stick is only 14 feet out, maybe 20 feet out, and you have to get that close to detonate the thing. And the blast can hurt you as well as the enemy ship. Submarines, there are about 24 to 30 submarines actually in the rebellion. They are almost universally death traps. This one, the Union submarine Alligator, is one of the few that never killed anybody. They only have one, possibly two successes, both on the Confederate side. So they're not really the answer they're looking for. What's very attractive are underwater guns, repurposing surface guns to be fired through ports in the hull of a ship. This is appealing because they exist and they're inexpensive. And you could make them work. The Navy, our Navy, the Royal Navy, and a bunch of private inventors are constantly in the newspapers talking about demonstrations of their guns. They can be effective, but again, you have to get within 20 feet. This 110-pounder Armstrong gun, the British managed to actually pierce a 21-inch hull in a test. But again, at 20 feet, your own ship has suffered a lot of damage from the enemy broadsides just getting in range. So it's a crude approach. It can be made to work. It's really not all that promising. The danger or the consideration is that people are trying to repurpose a missile designed to fly through the air with very little resistance underwater, and discovering the hard way that water is about almost 800 times more dense than air. This is a great picture of someone firing a pistol that should have gone, the bullet should have gone 900 feet. It hardly goes about 4 feet. Water just stops it cold because that missile, the bullet, is not made to go through water. All the energy it will ever have is given to it, is imparted to the bullet as it leaves the muzzle, and then it just decays. Hunt has a stroke of genius here. He realizes that the ram, Manassas in this case, is the weapon. I'm sorry, the ram is the weapon, not Manassas, the ship. All 387 tons of her iron, her machinery, the coal, the crew, its only purpose is to get that pointy beak ram into an enemy ship. He figures if I can create the ram without the ship, I have the weapon to reach Achilles' heel. How to do that is the challenge. Now, this is the one science slide, I promise you, and I'll get it out of the way fast and painlessly. Don't leave the room, please. Manassas was a kinetic energy weapon. And if that scares you, just remember a solid cannonball is a kinetic energy weapon too. It just hits with brute force, doesn't necessarily explode. The equation is that kinetic energy is equal to 1/2 the mass times the velocity squared. I promise you to be painless. It's just 1/2 times weight times speed, or how much punch it packs, or as I like to think of it, oomph. Right? That's expressed in joules. 1 joule seems a little silly. It's the energy supposedly required to raise a small apple 3 feet in the air. Think of it just as a unit of measure. It can be used to measure any energy. For instance, this SUV, which weighs 4,500 pounds, if it's going 70 miles an hour, is packing a punch of 1 million joules. It's a lot of power. Manassas packed even more. It's an effective weapon in that it did puncture the hull of Richmond, but it's not very efficient. It's packing 4.5 million joules of energy. And the reason why I say that's not efficient is that to puncture a 20 or 21-inch hull, which is pretty much the maximum in the 1860s, a little 12-pounder cannonball, which is no bigger than a baseball, can do that at almost 1,000 feet away with less than 1/4 million joules. So Manassas is way over the top at 4.6 million. It's 20 times as much power as it needs. And the Armstrong gun, again, 13 times more power than is needed to puncture the hull. These are over the top wastes of energy. There is a fourth option that several nations are toying with, especially the Russians. The British get a jump early on in rocketry when they go to take over part of India under Tipu Sultan, the Lord of Mysore, in 1799. He loses his kingdom, but he uses rockets against the British. The British are intrigued and figure if they don't like it, any future enemy won't like it either. And they task Lieutenant William Congreve to form a rocket corps. Within a few years, there are rocket troops everywhere throughout the British Army, all over the world. Now, a word about rockets at the time. Today, if we launch a missile, we expect it to hit right where we put the X on the map. We have wonderful guidance systems, GPS, all manner of technological ways to make sure it hits just where we want it to hit. At this point in time, no one is really trying to make rockets accurate. They have cannonballs for that. Trouble is, when you fire a cannonball at a body of men, believe it or not, in the Napoleonic period, and I think as late as the Civil War, troops had gotten pretty good at calculating or guessing the trajectory of a cannonball and simply parting ranks and then reforming. Let the thing roll through, no harm done. Rockets are a different story. Remember, your target is that body of men, a regimental square, and the officer's command and control extends only as far as he can be seen and heard, and as far as he can see his men. If you can disrupt that regimental cohesion, you've taken them off the board. A rocket does that in wonderful ways. For one, they sometimes bounce or graze. Ranges of British rockets were actually calculated by grazes, how many times you could expect it to bounce. They were totally errant. They did sometimes come back towards you, but not all that often. And they could flit all around, spewing fire wherever they went. And when they finally hit, they did explode. So if that comes anywhere near your regiment of men, your cohesion is just gone. Now, what makes these things so uncontrollable is their fuel. You've probably all been to Civil War, Revolutionary War reenactments and seen them firing blanks, cannons or muskets. When there's a plug in a barrel like that, either a cannonball or a bullet, the gunpowder, which is not compressed, comes out with a great amount of violence and pushes the projectile out the barrel. If, however, you form it into cakes, and these are modern cakes, but this is what they're using in rockets at the time. You can even wet this stuff, it doesn't matter, and form it into whatever shape you want. If you light it then, without having any plug in there, so it has an orifice to exit, that mass will expand 471 times in volume. So picture a gallon milk jug full of rocket composition, and you light it off, you now have almost 500 jugs of propellant gas. This is sort of what they're trying to control, and it's very, very difficult. I'm sure you've all seen the pictures of any spaceship launch where they show the engines vibrating and blasting back and forth. That's the kind of power that these fellows are trying to control, and why rocketry is such a challenge. The British do manage to use it, and some of these pictures are a little fanciful, especially the one in the top left there. They're not that accurate. They're good when you are going after an anchored fleet where they're all close together. The British do use it, sadly, to burn Copenhagen to the ground in 1808, and of course they tried to do the same thing to Fort Henry down in Baltimore. I'm looking at that picture, and I would not want to be a British rocketeer at this point in time. A lot of guys went home bald. The Russians, as I mentioned earlier, have been focusing on this quite a bit, and in their defense of Sevastopol in the Crimean War, they fired an awful lot of rockets. You'll notice that no rockets yet have any sort of fins or guidance. Sometimes there's a stick attached, but it's marginally successful. When they did hit home or even have a near miss, they could be very, very effective. One of these rockets launched from the city missed the British ship they were aiming at and went down under the hull and exploded directly beneath the keel. Now, water being incompressible just transmitted all that force of the rocket straight up to the ship. The British officers actually thought they had struck a rock, that had been hit that hard. It could have broken the keel of the ship with a couple more hits. Getting the things to go where you want them to go is the big problem. Over in the US, about this same time, an inventor named Pascal Plant, who has a variety of other inventions, makes what starts to look like a torpedo. It actually has fins in effect, and he's found a way, or believes he found a way, to launch it dry from inside a ship where the crew's protected, and as it hits the water, the scoop redirects it so it goes horizontally. Well, the scoop also misdirects it, and what's more, he hasn't solved the problem of what to do when your torpedo hits the wall of water, because that robs of a lot of energy right there. Plant does, in a demonstration, manage to sink a ship. Unfortunately, it was the ship next to the target ship, but no harm, no foul. The government wasn't interested. Now, Hunt's epiphany is, again, if the rocket is not the weapon, he's not going to make this explosive. It's just an engine. He wants it to drive the thing wherever he wants it to go. Wells is very, very interested. Within 24 hours of receiving the letter, he contacts Secretary of War Stanton and says, I want this guy working for me. So the Army lieutenant is now reporting to Wells, who reports to Lincoln. It's a very short chain of command. By mid-April, Hunt, who's been literally salivating to get away from the fort in Florida and to the front lines, is pulled from Virginia and sent to work for the Navy. He will be sent to the Brooklyn Navy Yard, where he basically has a blank check, don't ask questions, do whatever I want, for the duration of the project. The public gets wind of something going on at the Brooklyn Navy Yard. And I'm thinking from descriptions that probably up around here is where they're building this giant box. There's no secret about it. The Navy is building a box, and no one knows what it is. And someone, whether a civilian visitor or a sailor returning to the receiving ship there, the North Carolina, takes a piece of chalk and writes, what is it on the side? Now, to us, that sounds like a question. They also use it as a noun. For instance, explorers coming back from California with a new variety of plant would refer to it as a botanical what is it? An unexpected comet in the sky, a celestial what is it? So this is a name, and the name actually sticks. This is actually how I discovered this thing, was reading newspapers, and I saw the headline, what is it? And I asked that question myself and found out about rocket torpedoes. The public goes crazy trying to figure out what this thing is. They swear it's going to be a submarine battery. It must have a compressed air cannon. It's sure to be armor plated. We're going to sink it in the bottom of the James to fire upwards at passing ships. There's no end of speculation as to what this thing is. It really is just a box, a test bed. This drawing is made in 1872, from which I made the three-dimensional image over here of the way I think it looks. It's got a gigantic, like, 9-inch gun in there, but it's not mounted. There's no recoil to firing this rocket. They just need a metal tube to launch the thing. So it's mounted on a couple logs just sitting on them, and the Kentledge is like scrap iron just to keep the thing upright and weigh down the test bed. It has a primitive system of, a rubber band here to keep water out, and a port that can be pumped out after they fire it. And a man will go down and reload another missile, get out of the way, fire the thing, see what it does. By January of 1863, after a month of weather delays, it's horrendous weather, freezing and warming up, and in New York Harbor at that point in time, reports start to filter back that this thing is not working the way it's supposed to. Someone even said they saw it on the bottom, it's breaking up, it's unsatisfactory. They have no idea what's going on, but they're sure the thing is doomed. Until Valentine's Day, they bring it back, and Lieutenant Hunt reports an astonishing success. Whatever he's doing works. What Hunt has been doing is running trials of different designs of torpedo. And as we'll see, this wasn't by choice. He had a plan for what he wanted to do already. He's spending all this time proving to the Navy that the ideas they're forcing on him aren't going to work. He tries a variety of models, one with just propulsion out the stern, another one with lateral vents that spin the thing. There's some success to some of these, probably this torpedo with the lateral vents, because it travels like a bullet, spins, it goes faster. It made 250 feet underwater, which is impressive. Unfortunately, then it went up in the air and went another 150 feet and down again in an unknown distance under the water. Somewhere in the bottom of the bay, there's a lot of interesting scrap iron down there no one has ever figured out or found. What Hunt was proposing looked more like this. It's the same bronze rocket, but in an oak jacket with 4 grooves, 4 helical striations that go down the length of it. And the clue to this is he has an issue he doesn't identify. I think he's getting some lack of cooperation or some resistance from the Navy officers who resent him being there in late October of '62. And he just makes reference to the fact that all the trouble and time we took to economize in the rifling, as in to get out of doing the rifling, is not. That was tedious and trying, which means that everything they tried except the rifling didn't work. And this is tough to do. I've checked with historians out at Sturbridge Village, period villages like that. This is well within the capability of lathes at the time, but it still is labor intensive. And the Navy would like very much not to have to carve these darn things. Now, those newspaper reports are pretty much as far as most of the histories that mention Hunt will ever go. Because people took this report of failure, that report of failure, oh, this didn't work, oh, it's on the bottom breaking up. And rather than learn the whole story of what an elephant actually looks like, they each reported different aspects of it. So when you find Hunt's name in a history of torpedoes or submarines or the Navy, it's almost universally that, oh, whatever he was designing, it didn't work. Hunt is a scientist in this case first and a soldier second. All he is doing is conducting experiments, most of them against his will. He knows things aren't going to work right, the different models and that, and only by proving that his torpedo is the way to go does he deliver on time. 3 weeks after he returns, reporting a success. And by the way, that's not just opinion. There were Navy officers with him that had to, see what he had done. He's promoted. He had been promoted to captain just for time and grade a year earlier. Now he's promoted to major. This is not a reward for failure. There's a reason why he's being promoted. He's done something to warrant that promotion. And what's more, the project continues. The blank check still sitting there. There were a couple other projects at the time that I never understood why, when they were so close to success, the Navy pulled the plug on. My suspicion is that they are routing funding to the Brooklyn Navy Yard and Major Hunt's secret project. He calls his weapon a sea miner. And I believe he never is explicit about this, but at this point in time, geologists use what's called a soil auger. You could have up to a dozen different shanks that clipped on or screwed together, and you could bore down to find out what sort of soil was down there, or in some cases rock or coal, because his weapon is designed to corkscrew through the water like that. I believe that's why he calls it a sea miner. He never actually explains why. Middle of June, there's a final test, and we get our first look at what is probably the Navy's first torpedo tube or torpedo launcher. The newspapers are absolutely no help with this, because they say, well, there's a gun there of the strangest aspect imaginable. So picture everything you know about a gun, and that's not it. So happily, there is a drawing that seems to be from two different angles here, lateral and horizontal or vertical. And this is how I believe the launcher looked. This is an 1872 drawing, and I know that it's bronze. I know it's made out of that. It's got two different hatches, if you will. The front one up here is open to allow water in, so Hunt is launching wet, which is an advantage right there. He's not losing energy when he hits the wall of water. Once it's launched, that's closed again. The stern is open, the water just drains out. You load another torpedo, close the hatch, you're good to go. The final sea miner torpedo, Hunt has convinced him to go with the Oak, but here you can see why they wanted to bulk at that. It's not just that little test rocket. It is now 6 foot 5 inches long, 12 inches in diameter, and weighs just about 300 pounds. It is a massive weapon because, again, it's a kinetic energy weapon. Its punch is going to be its weight. On that day, officers of the Army and Navy went with him and basically said they signed off on it. The whole thing was perfect. It worked exactly like they wanted it to do. And by the beginning of July, the Navy Ordnance Bureau has put them into production. We are making rocket torpedoes in Washington or nearby. So why don't we know about these historically? Why aren't we using them to sink every single Confederate ironclad or taking on the Royal Navy, which has nothing like this? We should hear about Hunt and the fabulous, war rocket all over the place. Well, the hint why we don't hear about it is in this word here. Why are officers of the Army going out to evaluate a Navy torpedo? It turns out, I believe they want a dual purpose torpedo, because the report says also shots were fired from underwater to an astonishing height. Why isn't it shooting in the air failure? Remember back in January, some of the newspapers said that it wasn't working. Remember the one test torpedo that porpoised up in the air for 150 feet and went back down? That sounds like failure. In this case, they're saying this is exactly what we want. You have to remember that if the Navy is defending a harbor or a river mouth, launching a torpedo with the kind of speed we'll see this probably has can be sort of dangerous. If you miss that ship, I back up there, it's the Army that's launching them that close in. They don't want a lateral launch torpedo though, because if it misses the ship, it's going to hit a friendly emplacement across the river, across the harbor, or go into a town. And even though it's not explosive, a 300-pound weapon like this skittering up Main Street is not the way to defend your city. What the Army wants is a vertical launch weapon that can pack its punch and go right through all the decks of a ship and out the bottom of the hull. Now, Major Hunt knew there were issues with this, and he considered that all he needed was more time to perfect it. What Hunt is doing in late summer is making a range table. After the Napoleonic Wars, armies all over the world went to great lengths, armies and navies, to make range tables. What elevation, how much powder, what size ball. And they wrote this all down. So an artillery officer, ashore or afloat, had only to go to his manual and say, oh, it's that far away at this angle, pack in this much powder, that size ball will do the trick. The answer is right there. He doesn't have to sit there and make calculations. Hunt is trying to do this for his aerial launched torpedoes. Bear in mind, the Navy is already happy with the horizontal launch torpedoes. They're making the things at this point in time. Unfortunately, the repetitive tests and his workload, he's responsible not just for sea miner, but he is refurbishing or building fortifications in Narragansett Bay, in New London, and New Haven at the same time. Again, we are very worried. We are expecting war with England, and if they get past our fleet with sea miner torpedoes, we have to be able to defend the land. So all the engineering officers who aren't at the front are doing multiple jobs every day, trying to get all the forts finished or started even. Hunt is exhausted. He makes the rookie mistake of going up to light the fuse, which is called a Gomes fuse. It's basically fulminate of mercury impregnated string. It will burn 1 mile in about 1 second. He lights the fuse, but nothing happens. And he realizes in a heartbeat, he forgot to open the forward hatch. The chamber's not flooded. all the gas that should be pushing this thing lickety-split through the water is building up inside the launcher. And while it is stout, it's not meant to hold this. Hunt makes the mistake of rushing down the ladder to the interior of the what is it, hoping to open that front hatch. He doesn't make it. He's just about overcome by the gases because the stern hatch is ruptured. They're all spewing into the chamber. He manages to climb up far enough that he can be seen at the top of the hatch, waves for help, and then falls down. Several men in turn, I think 3 of them, try to get out to help him. Each one ends up passing out as well. One manages to get a rope tied around Hunt, but it's not tied very well. Others on the deck raise Hunt up. The knot comes loose. Hunt falls a second time. In one or both of those falls, he strikes his head on some metal fitting or leftover cartilage, I don't know what. He has concussion and compression of the brain. These are severe injuries even today, and really the only thing that even seems to help, despite all our high-tech science and medicine, is trepanning, the old Neanderthal approach to cutting out a piece of the skull to relieve pressure. It doesn't work, and 2 days later, Major Hunt dies. In a macabre twist I still can't fathom actually doing, the mangled launcher is offered to his wife. And I'm thinking, what was she going to do? Put it in her parlor, for God's sake? She politely says no, or at least a polite answer is what was recorded. She might have said an awful lot else. And Hunt is buried at West Point. The project is dropped. Nobody is available to figure it out. Others probably could have managed the range table. But again, all the engineers with the qualifications necessary are just so busy they can't spare anybody. A civilian gopher that worked for him said that Hunt would commit everything to memory. Every time they passed a threshold in the development of this weapon, Hunt would destroy everything. He was maniacal about keeping this thing top secret. And again, he's worried less about the Confederates and more about prying eyes of European spies. That's why the what is towed out in the middle of the bay for testing instead of doing it along the shore. So there's no paper trail to figure out what was going on. The Navy itself doesn't even know exactly what was being developed. That's how secret it was. They kept the secret from themselves. And so in that gap of historical information, it's the blind man and the elephant. Anybody's theory is as good as the next one. What exactly had Hunt created, and did it actually work? I was actually close to publishing this and needed some speeds and feeds, if you will. I needed some technical data, and I went to the Naval War College archives and was looking really for analogous information from an 1872 torpedo that I never did find. But in one of the books, I just chanced across Major Hunt's war rocket, and I found this beautiful diagram. And knowing the scale of the thing, I had measurements for everything and the interior of the torpedo. Hunt would probably roll in his grave to know it had been drawn this way, but you need this to build the things, and to know that it resurfaced. I expected a visitation. These had actually all been destroyed in December of 1864, so this is the only surviving drawing of his torpedo. The final C-mounted torpedo, and we break it apart, it's got a rocket composition core that will be lit from the outside. That's inside a standard bronze rocket, hollowed out, and the oak jacket that surrounds the whole thing and makes the whole device spin. The punch comes literally from an iron punch in the front. I think it's about 69 pounds. It's stabilized and held in place by a variety of spacers and liners. In the back, there's a ring of dense wood, lignum vitae, along with a bronze housing to keep the rocket dead center. There's a lot of force and energy going through here. Now, a lot of these are theorized. The different materials are indicated in that diagram. Unfortunately, the key to the diagram didn't survive. All I know is these are all different materials. The only thing I knew for sure was the bronze rocket and the oak jacket around the outside and that iron punch. Everything else, based on the color coding, is what I theorized. I did not use any exotic metals. I knew what was available to the Navy Yard. I found out what the weights of all these different kinds of wood were and where everything was laid out. So a lot of the metals here are my thinking. I'm open to suggestions. So how did this monster perform at 300 pounds? How fast did it go is the first question. It has to go fast enough to actually puncture a hull. In the 1880s, Lieutenant Sleeman of the Royal Navy wrote a treatise on locomotive torpedoes. And he realized that indicated horsepower, which is sort of a fudgy concept, but it's just a common number, if you will, a common denominator, a way to describe speed. And he realized that for the Whitehead torpedo, depending on its speed, that a factor of 2 pretty much indicated its its horsepower, if you will. And so using that factor of 2 based on speed, this is where it gets incredible and impossible. Hunt's rocket torpedo should have gone about 1,750 miles an hour, a veritable underwater laser. We know that can't be right, and this, proves the fallacy of indicated horsepower, but it's what they were thinking. Sleeman was a big advocate of rocket torpedoes, and if you think that went fast, you should see his data for a 24-inch rocket. Now, if it actually did go that fast, that's packing 41.5 million joules of energy, which is way over the top unnecessary. That's, like I said, 184 times the necessary power that's needed to puncture the hull. Hunt would not have done this as a scientist. It's a shameful waste of energy. There wouldn't have been a need to build anything this big. So we know that number is absolutely wrong. All he has to do is get this thing moving at about 130 miles an hour. That 300 pounds moving at 130 miles an hour will go right through a hull, just like the 12-pounder ball. Now, the actual speed is somewhere between these two extremes. Obviously, the 1,520 knots is ridiculous in a range of 5 miles. If it's going 112 knots or 129 miles an hour, we know the powder inside would burn out in about 10.5 seconds. That gives it a range of about 2 football fields, which is respectable, considering in 10 seconds you're going to have a hole in your ship. Now, balance is another thing, because all the aerial missiles had problems with balance. That was one of the things people liked about them. They would go haywire and skitter around the sky and the field. In this case, you wanted to go hot, straight, and normal, to use the modern expression. The first thing about balance is displacement. Displacement is the volume of water that a mass in that water pushes out of the way. If the mass of the diver on the left or the submarine on the right is equal to the weight or mass of the water that it has displaced, it will literally hang there, as you see she is doing and the sub is doing. This allows them to hover in place. Now, a 299.5-pound torpedo displaces a little more than 4.5 cubic feet of water. 4.5 cubic feet of water weighs 0.65 pounds difference. Hunt's torpedo has what's called neutral buoyancy. It will simply sit there and float at depth. It has perfect displacement. Now, what about balance? Balance is affected by fuel consumption. And again, in an aerial rocket, as the fuel is consumed, it gets nose heavy. That's fine. You want it to go down after you send it up in the air, because that's where the target's at. Not a good idea for a torpedo. They're just going to hit the bottom all the time. Calculating how fuel consumption affected performance was a bit of a stonewall for me at first. There's a little funky science here, but for any researchers in the audience, I think the methodology will stand. I took the weights as I posited them for the torpedo and sliced the whole thing into 1-inch wafers, if you will. So at every 1-inch mark, I knew how much that wafer weighed. Now, if we can get the center of figure, which is where you say, where's the middle of the thing here, identical to the center of balance, that means it's going to stay perfectly level at the time. The problem is the fuel. I wasn't sure. I spent a lot of time online checking different scientific pages, saw more seesaw diagrams, where you have a balancing point in the middle and how far forward does a heavier kid move or a light kid move to weigh them, balance them out. And there was no way to calculate 77 inches, 77 plot points. And finally, after days of looking for anything that would work, I found one scientist who at last was honest enough and said, yeah, when it gets this complex, we just have to build it and test it. And I thought, I can't possibly build a torpedo. But much to my wife's amazement and surprise, I built a balancing board. This board is 77 inches long, measured off in 1-inch increments. And even though it might be bags of nails or empty wine bottles with a certain amount of water in them or an anvil, every one of the gaggle of things hanging at every 1-inch point has been weighed on an aircraft luggage scale down to 1/100th of the precise weight at that time. So I now had a torpedo I could balance and see. This not only trashed my workshop, it almost ruined that sawhorse because it wasn't designed to hold 300 pounds of stuff. I found that the fuel level, of course, whenever it's just sitting there at 100%, the center of gravity is a 1/2 inch off from the center of figure. It's perfect. When 1/4 of the fuel is gone, it's spot on. When the fuel is half gone, it's off by only 1/4 inch. And when it's almost all gone, it's spot on again. And when it's empty, it changes by 1/2 inch. The fuel, the way he has it molded and configured, burns from the inside out. So the balance, the weight changes universally or uniformly throughout. It doesn't affect the balance of the thing. So how did they make this thing go high trajectory? Well, when I first built that balancing board, if you want, or my mock torpedo, I placed the weight that you see here right where it showed in the middle. And I realized that that just made the thing go nose down. And I thought, well, why would they do it that way if you can't make it level? And when you blow up the diagram of this, though, here's the weight now. If you look closely, these aren't wood screws. They're set screws. You notice how they're flat down here? They're meant to impinge upon the bronze housing, not pierce it. You should be able to loosen those and move the weight. So I did that. I started moving this back further and further and further, and every 6 inches, the nose didn't come up. It just stayed right down like this. And I thought, great, this is going to fail. The weapon doesn't work. I can't prove that it would ever balance horizontally. And I just kept moving it back further and further and further until when it was all the way at the stern. And the second I moved the weights back to the stern, the nose came up and the whole torpedo, the whole board, leveled out perfectly horizontally. That's the only way that the Navy could use the torpedo. But if you nudge it further and further forward, it makes the nose of the missile go down faster. So if I'm an Army gunner and I look at my range table Major Hunt has created, and it says, okay, when a ship crosses that point there, launch your missile by pushing that weight forward X number of inches, and it will nose down fast enough or weight long enough to nose down to strike the ship and puncture its hull. I think that's proof of the high trajectory capability. The missile could be used aerially or, like I said, a horizontally launched underwater torpedo. This looks to be a perfect rocket torpedo. Hunt had succeeded in something that nobody else had managed to do. Based on all these calculations, it has perfect displacement. It has perfect balance from launch to fuel burnout. There is no reduction in speed, unlike the bullet, to which all the energy it will ever have is imparted when someone pulls the trigger. This carries its own fuel with it, and it won't slow down until it's totally out of fuel, which will happen down 2 football fields. The range, again, 2 football fields long, takes it 10.5 seconds to run that at 129 miles an hour. You can't get your ship out of the way fast enough. And if it's 300 pounds and moving at that speed, it can go through just about any hull on the planet at this point in time. 20, 21 inches is the max. Other indications of success, this is funded for 18 months, whereas I mentioned other projects are dropped. The weapon passes its trials in January and February. Hunt is promoted to a major as a reward for those efforts. And the June 63 trials are considered to be entirely successful, and they're starting to build the things. We have these in production somewhere. So why is it dropped? Why don't we hear of Hunt's C minor? I've asked a lot of people this, and no one has a really good idea. There were very few people aware of the project. Hunt is the prime mover. Certainly his death means nobody else can finish it. There's nobody available to complete the range tables. As I mentioned, the engineers are all too busy. There may have been inter-service rivalry. He has monopolized the Brooklyn Navy Yard for months, for more than a year. And I think Navy maybe didn't want to pursue it. I don't know, because it's already in production and proven to work for them. It shouldn't matter if they can't use it aerially. It could also be that the threat of global naval war is passing. We're winning, putting down the rebellion. Maybe we decide we don't need the thing. In December of 64, all the rockets are basically tied down and burned out and destroyed down at the Washington Navy Yard. We don't save them for after the war or anything. We focus on the spar torpedo, the bomb on a stick. And so our first torpedo station at Goat Island in Newport, in Narragansett Bay, we're developing spar torpedoes instead of rocket torpedoes. In 1874, inquiries made at the Brooklyn Navy Yard really turned up nothing. A couple of people who still work there made those sketches, which have their limitations, but no one could even really say what it was that had been developed. It was that secret. Like I said, the Navy managed to keep the secret from themselves, even while funding it. I was almost going to call the book The Civil War's Last Secret, but I guess you can never really say that because there could always be something else out there. But Hunt's maniacal insistence on secrecy lasted 150 years until I found that stray reference to the what is it. And I know the date because it's my son's birthday. It is certainly, if not the last secret, the best kept secret of the entire war of the rebellion. No one will be able to do this again until the waning days of World War II, to launch a missile from underwater and have it go through the air to attack a target. The German Navy manages it with a V2, and happily they didn't get across the Atlantic. They were going to tow a V2 behind a U-boat and get out of the shipping lanes and deploy the launch platform so the V2 went vertical and launch it to strike New York City. We captured that scientist, and in the early 50s, developed the Polaris missile system, where we were launching an aerial missile from a submarine. It had been about 80 to 90 years since Hunt had first done it, and it took us that long to catch up. I'm sure there's going to be a lot of questions after this presentation, so I thank you all for watching. I hope you enjoyed it. And Mike, we can move on to questions now.